This talk is on late divergence analysis, and it will cover how to detect machine regions where threads diverge. So by the end of the talk, we should be able to answer the questions, are all threads enabled at this point? Is only one thread enabled? And if threads diverge, where do they diverge? Where will they converge? So I'm going to start with a motivating example that this analysis is useful for, and then I'll cover the existing LLVM support to access this type of information, and finally I'm going to walk through our custom pipeline for generating this analysis. So let's consider a SIMT machine. And this is a common type of architecture that's used in GPUs and other special purpose architectures. So SIMT, single instruction, multiple threads. So this means that during program execution, there's a given number of warps that can each be executing in a different instruction. They have their own PC. And then in each warp, there's a set of threads, and all the threads share that same PC. They execute in lockstep, but they can have different local data. So if you look at warp 2 in the diagram, all of its threads are executing at that same if statement, but they may have different input values for I, count, etc. And so they can disagree on the branch condition, even though they must all branch together. So the way that this divergence is typically handled in machine code is with predicate flags. So each thread in a warp has an associated flag that controls whether it's enabled or disabled at a given point. And so you can imagine these predicates can add considerable complexity to the generated code. So let's think about a sample program that might run on this type of machine. And we can think about a simple producer-consumer algorithm. So each run iteration, warps are partitioned into producers and consumers. So that's a warp-level divergence. And then internal to those routines, there can be some additional control flow that's either divergent at the warp or thread level. So if we take a look at the producer code on lines 4 and 5, we can imagine some iteration condition where threads continue to produce until they're done. But how much they need to produce might be dependent on the thread. So maybe the work was spread across the threads, but it didn't split evenly. And then we can take a look at the consumer code on lines 8 to 10. We have that same outer looping behavior, but there's some additional inner logic. And for the sake of the example, let's say that it's not thread dependent. So for instance, anytime a warp needs to consume data, it may have to check that it's buffered beforehand. And so you can imagine this arbitrary layering of warp and thread dependent logic. So from this example, we get this control flow graph. And we have an outer run loop and then an inner if and else, so to produce or to consume. And then inner to those routines, we have some additional control flow. So how do we generate SIMT compatible code for this case? So typically, predication is handled by collapsing the control flow and then computing a predicate for each block or set of blocks that controls if a thread is enabled during its execution. So here we have an example of such collapsed code. And you can see that the entry and loop header fall directly into the producer routine first, and then that falls into the consumer routine after that, with the warps looping back, as long as any thread still needs to execute one of those routines. And then finally, they'll fall into the barrier or exit. But if we remember from the example, a lot of the branching logic is warp dependent and not thread dependent, and warps are free to diverge in execution. So for example, the branch, to produce or to consume, that's done at the warp level. And so ideally, in the generated code, we'd like to use those branches directly instead of the predication. But how can we know that it's safe to do that? So LLVM has a built-in divergent value pass, and this is over the IR instructions. Targets will specify divergent sources, so things like thread ID, iteration variable, maybe memory. And then the path propagates that divergence to dependent values, so to either data or sync dependent values, as shown below. But what are the limitations of this? So this is only accessible in the IR and not on machine instructions. It's also done at the instruction level, and so not at the block or region level. And so we can't quite answer the questions, are all threads enabled at this point? Is only one thread enabled? So to support this full analysis, we built a custom pipeline depicted here. We start on the IR code and we take in, that LLVM divergence analysis, and we tag any branch instruction that's known to be uniform, so the opposite of divergent. Then, to preserve that information through selection, we generate pseudo machine instructions and add them to the blocks that have uniform branches. Then those pseudo instructions can be picked up by our divergent region analysis. Now, LLVM has a concept of regions already, and that's something we draw on in our region analysis. And I'll go into more details about that in a further slide. But the output of our divergent region analysis is a nested region hierarchy with divergent, uniform, and other properties attached to them. And that's something that can be picked up by our predication algorithm and other optimization passes. So as I mentioned, LLVM has a concept of regions, and this exists both at the IR and machine level. It's based on the program tree structure that's described in this paper from 1994. And the idea is that it detects single entry, single exit regions that are bounded by an entry and exit block. So an entry and exit blocks are found through control dependence equivalence. And put simply, that equivalence means that if one block is known to execute, then all the equivalent blocks are also known to execute. They're dependent on the same control edges. So on the right-hand side, the blue blocks are control dependent equivalent. And you can see that they help create the boundaries for the 3 regions that are identified. Now, it actually turns out that we needed to implement our own region analysis, but it's based on these same principles. The reason we needed a custom analysis was to increase the granularity of the regions detected, and also to support a modified control flow graph when necessary. So once we've identified these regions, we want to attach the divergence property to them. So we can define a divergent region as a region where the threads diverge from its immediate dominator region. So just like blocks have an immediate dominator, we can think about regions having them as well. And so a divergent region means that at the boundary of that region, there's a potential thread divergence. And so the way that we compute this property is similar to the LLVM divergent value pass. We start with sources of divergence. So any region that has an incoming divergent edge is marked as divergent. Then parents propagate that divergence to their children, except when either of these 2 conditions are met. So one condition could be a child dominates the divergent sources, those original divergent edges. And in this case, we can think of the divergence as being resolved, and so it doesn't propagate to the child. Or the parent region could dominate the child. And in this case, we can think about the context being reset. So the child isn't diverging from its immediate dominator, that's the parent in this case. And instead, nested inside the divergent region of the parent is a uniform child region. And we'll see an example of this when we look back at the producer-consumer algorithm. Now, in most cases, one of these 2 conditions is met, and the divergence isn't actually propagated. But there are some cases where it is, and that's usually for more irregular control flow, something like a switch statement or a goto. So the result of our custom pipeline is a set of nested regions where each region is either divergent or uniform. We can actually go a step further than that. If we think about regions where every dominator in the dominator tree of a region is uniform, then we know that the threads will never diverge from the function entry to that region. And so here I call that function uniform. If we think back to our motivating example, this is the control flow graph that we had, and these are the sources of divergence. So our analysis will produce these uniform regions, or these regions. So there's 2 outer uniform regions, and then so that's including the run loop, and then there's 2 inner divergent regions for both sides of the if. And the divergence comes from their divergent loopbacks. And finally, inside the consumer region, we can see that we have a uniform region for the buffer check. So now when we go to admit the predicated code for our SIMT machine, we only need to produce predicates for regions that are marked as divergent. And additionally, we can leave in all the uniform branches. There's a slight caveat. Branch heads need to be restricted so that they don't jump past regions that they don't dominate. And this is something that's layout dependent. So thinking back to our original predicated code, where we used predicates in the outer run loop and fell from the loop header to produce to consume, now we can safely remove those predicates and use direct branches instead. There are some other applications we came across besides predication for our machine. And so one example of that is hardware loops. In our case, machines require that loopback conditions for a hardware loop are uniform. And so this analysis helped us identify loop candidates. Another case was tail call optimizations. When we identify tail calls that happen in a function uniform context, then we're actually able to apply the standard tail call optimizations to them. And finally, we added one extension to our analysis pipeline, and that's thread uniqueness. So oftentimes, there'll be logic in an algorithm that only needs to execute by a single lead thread. A unique property can be identified and propagated similar to the thread divergence. And this is something that's very powerful in predication because once only one thread is enabled, then all nested control flow will be uniform. That's it. Thanks for listening.